Thank you very much for the introduction. And my name is Koya Shimokawa from Autonomous University. And I'd like to thank Enzo and the organizers for giving me a chance to talk in this nice conference. I'm a topologist and not theorist, and I used to be a Saitama University, and I moved to Autonomous University this April. That is a small women's university in Tokyo. So I'm from Tokyo now. So today, I'd like to talk about untying pathway of vertex knot. So the motivation of my research is this experiment. This is a paper by Irvine W. And actually, DeWitt informed me this very interesting paper to us. So at that time, I was considering recombination of DNA. And here, we see the similar pattern. So here, we will consider the reconnection. And we will see the similar situation of between the reconnection and the recombination. And actually, I found that our result of the DNA can be applied to this situation. So that is the motivation of this research. So I'd like to explain how I will consider this problem. So I'd like to give the mathematical model of this and consider the topology change of the reconnection of the vertex knot. Okay, so in this talk, we'd like to characterize untying pathway. So starting from a knotted vortex, at the end, we assume that we have unknotted a knot or maybe unknotted link. And we like to characterize how it happens. So we like to characterize the pathway. And the reference of this talk is these two. And actually, this paper is on DNA. But the mathematical part, we can apply those to reconnection. Okay. So I'd like to first introduce some basic terminology. I think all of you know that knots is just as one component. So we can consider it as an embedding of the S1 into R3 or S3. And if you have multiple components, we call it link in this talk. So you have 2-component link and 3-component link and a 4-component link. And due to the technical assumption, in this talk, we only consider a knot and also a 2-component link. Maybe the component number is more than 2. I think that will be a future problem. Okay, and this picture is generated by Notplot. So in this paper, so they made a beautiful torofoil vortex knot. And also observed that by a reconnection, the topology will be changed. And first, you see a torofoil here. So this is a timeline and torofoil here. And that will be changed into a hop link with one reconnection and will be untangled. And we like to characterize such a pathway. To do that, we need to give a mathematical model of the reconnection. And after that, we will apply knot theory to characterize the pathways. That is what I like to do today. Okay, so the aim of this talk will be give a not theoretical model of reconnection. Actually, many of the person here, including DeWitt and Enzo, also already talked about the not theoretical model. So, but today I'd like to give a band surgery version of the reconnection model. And using that, I like to characterize the pathway of untying vortex knot. So here we only consider the case where the topological complexity will be reduced. And after that, you have a knot to unlink. And if you consider, of course, there is a situation that the topological complexity go up. Sometimes you might apply my result to that case, but in those cases, there are more possibilities. So you might have other pathway. So you have to be careful. So today, we only consider untying direction. Okay, and the main aim is that I like to explain this picture. And this picture is appeared in one of the reference in its paper appeared in the scientific report in 2017. And so this gives pathways, and actually we characterize the pathways. But to do that, we need a mathematical model and several assumptions. So I'd like to give you what is the assumption to this result and what is the result we have. So I'd like to do that. Okay, so we come back to this picture later. So to do for this, we need a closing number and also a signature that will be introduced later. Okay. So first, I'd like to give the my mathematical model of the reconnection. So we like to consider the topological change, and so today we say that vortex not a link. That means the center line of the vortex tube, and the topology will be changed like this, and by reconnection. And here we consider the orientation of not a link. Sometimes we think that non-orientable, not oriented link, not a link. But in this talk, the orientation is important. So, and the orientation comes from the direction of the the flow. So when you have a vortex, not a link, I think you can naturally give the orientation of the vortex. So we use that. And actually, so maybe it is not easy to see, but here you see the arrow. That means the direction is followed. So this is oriented trefoil. And here you can see this direction and this direction. This is oriented hoplink and so on. So today, every not a link is oriented. Okay, so this is a mathematical model of reconnection. So if the reconnection, so these are the typical type of the reconnection. You can use tangle and the tangle surgery to a model of the reconnection. So in this case, the zero tangle is changed into -1 tangle or +1 tangle. And if you change the position of the eyesight, then actually this is ambient aspect to this one. So here you have so please be careful with the orientation. So you have the parallel direction orientation here. And if you have anti-parallel orientation, and if you do the reconnection, you have this picture. So this is a tangle surgery model of the reconnection. And for my case, I use band surgery, which I'll define in the next slide. So here is a part of the knot or link. And this is a band surgery. You prepare some band, and using band, you do some local move. And after that, you will have this. So this is the same picture as this. And also, if you and also, if you have this situation and you do the band surgery, you have this picture. So I'll give the definition of the band surgery. So the band surgery is defined by giving a band. A band is just an embedding of the square or rectangle or something like that. So you prepare interval, and interval time interval give you a square, and you consider embedding of that in a three-dimensional space, and we assume that two sides meet knot, and the other two sides doesn't meet a knot. So here a square is embedded in a half-twist way, and this side and this side meets the knot, and this side doesn't meet the knot. And what we do is that remove the so in this case, sorry, I made a mistake. So this is the original knot. And if you embed a band, then this part meets this part, and this part meets this part. And this part doesn't meet these not. And you change by removing this meeting part to these other two sides. Then this band gives you the reconnection, and this part is changed into this, and this part is changed into this. So this is one model of the reconnection, and in knot theory, this operation is called a band surgery. So I will use this as a mathematical model of the reconnection. Okay, and the band is denoted by B, and if you start from a oriented a link L, the obtained one is denoted by LB. Okay. And as I said before, the orientation is important in my talk. And if the band surgery preserves the orientation outside, and in that case, the band surgery is called coherent band surgery. The definition is as follows. So here you see a part of the knot or link, and that will be changed by a band surgery as this. And suppose that the orientation, so you have some structure outside, and if the orientation is preserved outside, then that is called coherent band surgery. And actually, there are two types of the band surgery. One is coherent, which preserves the orientation. The other is incoherent, and that is not that does not preserve the orientation. So this is a picture of the one example of the coherent band surgery. So here you see oriented torus, so in this direction. And as a result, you have this by a coherent band surgery. And if you take a look at the orientation here, so if you take a look at this part is oriented this way from right to left. And as original, so that part is correspond to this part. This part is also oriented from right to left. So in this example, the orientation outside of the band is preserved. So that surgery is called coherent band surgery. So we will consider this. Actually, when you consider the reconnection of the vortex knot, we assume that the reconnection is coherent band surgery. So we will use this. Okay. And the first observation is the following. So if you consider a coherent band surgery, then that will change the number of the component of the link. So that is a very important observation. Suppose you start from this link. This has a two component, torus link, 2,6 torus link. And the orientation is parallel. That means that the blue line is directed in this way, and the orange line is directed in this way. And we call that orientation is parallel orientation. And if you do a band surgery, a coherent band surgery, so in this case, this part is changed in this part. So this part is changed into parallel part. Then you have 5-1 torus, 2-5 torus knot. Then, as you see, the number of the components is changed. 2 will become 1. And if you do the next step, then you have 2 components. So if you only consider coherent band surgery, if you do the band surgery, every time the number of the components will be changed. So that is the important thing. So you have link, not link, not. So that can be proved easy way. So this is a part of the link. And if you go out, then it has to go back. But if you consider the orientation, that will come back this way, or that will come back that way. If you come back this way, then this will connect this way, and you have a knot. And if you come back this way, you have a link, and in that case, you have 2-component link. And the outside is preserved. So if this part is connected this way, then that will come this way. So in that case, you have a knot, you have a 2-component link, and so on. And actually, that is applied to a multiple component. If you have 3-component link that here, then you have three component, then you have two component or four component. The component number changes by one every time. So this is a model of the reconnection by using a coherent band surgery. And using this model, we like to characterize the unknotting pathway. Okay, so if you do this model, and this will be the problem you will consider knot theory. So one problem will be the first one, given the topology of the vertex and characterize the untying pathway. So suppose you have this as a vertex knot or link, and at the end you have the unknotted vertex, and what you have in the middle. So that is one problem. And the other problem is that characterize the place where the reconnection happens. So as I said before, if you do the reconnection here and deleting this crossing, then you have this as a result. And the next problem is that asking that, is there another way, another place where you can do the reconnection and have the same result? So that is the second question. And I like to ask those problem in this kind of example. Okay. And to do that, if you consider it pure mathematically, actually, we can probably say that there are infinitely many pathways from this one to this one. Maybe the complexity goes up and go down to have a knot in the end. So we need a good assumption to have a finite number of the pathway. So you need some good assumption for the characterization. So in this talk, we use this assumption to give a result. So first assumption is that we assume the number of the component of the link is 1 or 2. So here in this talk, we only see knot or 2-component link. So in general, maybe you see a 3-component link, but that will not appear in this talk. So that is one assumption. The second assumption is that topological complexity. So we assume that topological complexity goes down or stays the same when reconnection is applied. And for this talk, we will use crossing number as a topological complexity. So we assume that each reconnection, the crossing number does not increase. So it stays the same or goes down. So that is the assumption in our talk. Is it okay? And for the second part, so I will divide it into two. So first we consider the case where each reconnection strictly reduces the crossing number. So that is the first assumption. And then in the next step, we relax the condition and we assume that the crossing number can stay same or going down. First, we consider the very strict assumption. And using that assumption, we will characterize the pathway and also the place of the reconnection that we like to do. And here we consider the case of the topology of the vortex knot is a special case, torus knot or link of this type to P. And I don't know how strict this restriction is, but I think you see this picture in Mark's talk today. So I hope this is not so strict, but so here we only consider the case where the first topology is this type to N torus knot or link, and consider the untying pathway. Okay. So if you consider a 2,6 torus link, which has 2 components, and suppose the orientation is parallel, and we like to consider the product of the vortex knot or link by reconnection. And if you start from a 2-component link, under our assumption, what you have is a knot, so oriented knot. And and we assume that, and here we assume that the knot has at most 5 crossing. And the reconnection is something like this. So that is one problem. And for this, we can give a complete answer to this. And the answer is the following. And the answer is that what you have is a torus knot 2, 5 with this chirality. So that is the first result. Okay, so if you think about this is the first step of the reconnection, and we like to consider the next step of the reconnection. So next, consider the topology of the vertex knot is this one. And you assume that the reconnection is a band surgery of this type. And also assume that, so this is a two-component link. And we assume that the link is at most 4 crossing. And what we can show is that the product will be this one, a 2-4 torus link with parallel orientation. Okay. And actually, in general, we can do the same thing. So first, we assume that the first topology is 2n torus link. So n can be anything. So you might have maybe 100 crossings. And the assumption is that reconnection is a coherent band surgery. And we assume that the crossing number actually goes down. So if you start from 100 crossing, we assume that this node has at most 99 crossing. That might have maybe 3 crossing or 5 crossing. And any crossing number is okay. But we assume that the crossing number actually goes down. And what we can show is that you have a unique topology as a result. And if you start from a 100 crossing, then you have a 99 crossing torus knot. So that is the result. Okay. And for the next step, if you start from 2 to n torus knot, so this is a odd integer, and you have a torus knot, then we assume that the crossing number actually goes down. Then in this case, too, we have a unique topology as a result. The result is that the torus knot of this type and the crossing number go down by just 1. So in this case, if you assume that the first topology is in this type, we have beautiful result. And every time the result topology is unique. And you have just one pathway. So that is the result. So you can say in this way, suppose the reconnection is a coherent band surgery, and you start from this link, and assume that each time you reduce the crossing number, then at the end you have the trivial knot, and we can characterize the intermediate. And the first step you have torus. If you start with the torus knot link, then you have a torus knot of this type with 1 less crossing, and go on. So as you can see, this also gives the number of the reconnection you need to untie. So if you start from a 6 crossing knot, then you have a 6 crossing link, then you have 5, 4, 3, 2, 1. But actually, the 2 will go to 0. So you need 5 steps to have the trivial knot. So here is a picture, 1, 2, 3, 4, 5 steps. And actually, in a different way, we can show that this is the shortest pathway. If you start from this topology and do the reconnection, and actually you need 1, 2, 3, 4, 5 steps to have a trivial knot. Okay, then next I'd like to explain the number of steps you need to have a trivial knot. For that, we need a signature. And to do that, I'd like to give you a very basic, not theoretical argument that is in the textbook. For that, we need a Seifert surface. And using the Seifert surface, we define a signature of the link. So Seifert surface is a compact orientable surface, which is bounded by a given node, oriented node, or link. And actually, if you have a diagram, there is a good way, Zipf's algorithm, to have Zipf's surface. So the important thing is that the link is oriented, and you have the Zipf's surface is oriented and you have this as an oriented manifold. So orientation is important. These two. And if you have a Zipf's surface, you can define a signature. And what you do is that you take a basis of a one-dimensional homology. So if you have this picture, then A and B will give you the basis of the one-dimensional homology. And you will consider the linking number. First, you choose 2 and consider the linking number of this. But if you don't move, these two will be intersect. So you need to move it to make a link. In this case, you will move just a little to the plus direction of the Zipf's surface. And that is, if you move it, move A to the plus part, that is denoted by A plus. And you will consider this type of the matrix. And that is called Zipf matrix. And in this case, you have this as a Zipf matrix. And so that is denoted by M. And the signature is defined by yes. So you prepare a Zipf matrix and consider the transpose of it and consider the sum of two matrices. And you have a symmetric matrix, and you consider the signature of the matrix. That is called the signature of the link. And the signature is defined by a number of the positive eigenvalues minus the number of the negative eigenvalues. So in this case, for the trefoil, you have this, and the eigenvalue is -1 and -3, so the signature is -2. So actually, you can calculate the signature, and it is known that the signature is a link invariant, and that is important in a situation due to a theorem by Murasugi. So it is known that the reconnection only changes the signature by 1. So that is at most 1. So that is a theorem by Murasugi. So if you take a look at the signature, so you can guess how many reconnection you need to untie it. So that is our idea. And for the proof of the theorem, what I explained before, we showed this proposition. So we give a relation of the signature and the crossing number. And this is an inequality we have in general. So this is the absolute value of the signature. And that is bounded above by the crossing number -1. And we know that if the equal, we know the case where the equal holds, we can also characterize the knot. And in this case, you have the torus knot or link of this type, 2CL. And if you have a two-component link, then we can also show that the orientation is parallel. So this is very special, and in this case, we can apply this to have a good result on this. And using this, actually, we can give proof for the 2-6 case, just like this in maybe two line. Okay. And so I think the idea of the proof of the theorem comes from this proposition. And we can also argue that this proof of this proposition is not so hard and using only this. So you need information of the Zipf's surface that is obtained from a diagram. And what we do is, so now consider the number of the Zipf's circle and the crossing number, and you can calculate the Euler characteristic of the Zipf's surface. And you give the relation of the Zipf Euler characteristics and the signature, and you have some inequality, and you have the proposition. So it's not so hard. Okay. So so if you assume that the topological complexity, in our case, the crossing number goes down every time, then you have only one pathway. So the pathway is unique. But if you relax assumption just a little, then you have actually many pathways. And this is a new assumption. So the next assumption is that the crossing number does not increase. So it can stay same or go down. So that is a new assumption. And we only consider the case where the first topology is 2,6 torus link. And in that case, we have 9 pathways as a result. And if you like to go further to consider the case where the first topology 2,8, I think you have 200 something pathway by simulation. And we haven't finished the proof that is all or not. So so if you consider maybe 2,8, then you have a little complicated. Okay, so and also this assumption is very important. If you remove this assumption, there are infinity many untying pathway. So if you allow the crossing number goes up, then the things will be very complicated. So you need some assumption. So this is the result we have. So, so first topology is 2,6 torus link with a parallel orientation. And this arrow means a reconnection. And we can show that, so we assume that the unknot is obtained in 5 steps, or unlinked in 6 steps. Then there are exactly 9 pathways, which satisfy the assumption that the crossing number doesn't go up, and so on. So this is an explanation of this picture. And as you can see, so in here you see the signature. So signature of this link is -5, and at the end you have a signature 0. And if you like to think about the shortest pathway, every time the absolute value of the signature has to go down. So we can assume that the next step you have the signature is -4. And we also assume that the crossing number stay the same or go down. So if you start from the 6th crossing, you have 6 crossing or 5 crossing or 4 or 3 to 1 here. But this shows that in the first step, there are only two possible product. And the first one is that the projected sum of 2 torus. And the second one is a 2,5 torus link, torus knot. And if you assume the crossing number goes down, then the pathway is this. So 6, 5, 4, 3, 2, 1, 0, 2, 0. And if you allow that the crossing number stay the same, then you have 6 crossing knot in a first product. And in the second step, you might have 6 crossing link. And we show that this is only the pathway. Okay. And so there are red arrow and blue and black arrow. And for the red arrow part, we can also characterize where the reconnection happens. Okay, so this is the explanation of this picture. And I'd like to give the idea of the proof of this result. So first, as I said before, the signature in an intermediate can be characterized. So this is the first information to get rid of the other many knots and links in the as a candidate of the intermediate. And we can also show that the split link doesn't appear in our case. If you start from to 6 torus link, everyone here is not split link. So you only see knot or non-split 2-component link. That's good. You can show it using a signature. And in the next step, So we know, so we only consider the not a link up to 6 crossing. So there are only maybe 20 or 30 candidate, and you can characterize, calculate the cross signature, and this is the candidate for the first step product and second step product and third step product. So you have this, and you check whether actually there is a reconnection between the so this is the first topology, and you check whether there is a reconnection from here to there to here to there, or maybe here to there or something like that. And actually, there are only few which have the reconnection. And to do that, we will use some not invariant. So this is a result of Kanenobu. And you can have information of the reconnection by using special value of Jones polynomial. And if you have a not and so that will give you the information of the Jones polynomial as a product. So this one is the first topology, and suppose you have LB as a product. And in that case, the special value of the Jones polynomial satisfies this. So by calculating Jones polynomial, you can get rid of some candidates. And also, a Q polynomial can be used for this, and this is a result by Kanenobu. So we will use this, and also alpha invariant. You can use alpha invariant. And so using this not and link invariant, we have this picture. So if you use only crossing number, maybe the candidate will be thousands or maybe tens of thousands pathways, but using those, you can reduce into 9. Okay, so that is the result. So, but here we assume that the crossing number goes down or stay the same. So that might be a too strict condition. Maybe sometimes the crossing number goes up and goes down to have a not in a shortest pathway, but that pathway does not appear in this picture because to our assumption. Okay. Next, I'd like to discuss where the reconnection happens. Okay, so this is a case where the reconnection will turn the peripheral node into a hop link. And we can show that this is the only case up to isotopy of the band surgery. So if you use the band surgery as a model of the reconnection, then the uniqueness comes from the ambient isotopy of the band surgery. So if you do the ambient isotopy, then you might have a little complicated picture. But our theorem says that if you do the ambient isotopy, then this is the only picture you will have after ambient isotopy. So in that case, we say it's unique. Okay. So this is a reconnection. And to do that, actually, we use this theorem, which is proved by Sharman Thompson in 1989, and Hirasawa and myself 2000, and Durrell, Miyazaki Motegi, and I forgot the date, but so here we use the Zyphus surface, and we show that if you have a band surgery, which reduce the crossing number, which reduce the complexity. So in that case, the complexity is the Euler characteristic of the Zyphus surface. Then we can characterize where the band is. But we don't go into detail of this. But this is theorem we will use. And If you consider next step, suppose you have a hop link, and by a reconnection you have a trivial knot, then we can also show that the place of the reconnection is unique by a theorem of Thompson and Hirasawa and myself. In this case, it's also unique. And if you consider a next step, in this case, we assume that the trivial link is obtained from a reconnection of the trivial node. We can also show that the place of the reconnection is unique. So in this case, reconnection happens in this way. Okay, so this is a theorem by Sherman, 1985. So when you consider this pathway, we can say this part is unique, and this part is unique, and this part is unique. So you can determine the place where the reconnection happens. And actually, also, if you consider this pathway, we have a characterization of the band surgery from each pair, from torus not link to this torus not link. Reducing the crossing number by 1, we can characterize the path, where it happens. So suppose you have 2p torus not link, then the reconnection is something like this. You will do a smoothing at this crossing. So this is the result of 2016. Okay, so this will give the where the reconnection happens. And we also have a little complicated case where the starting from a torus knot and have a composite correct sum of torus knots, then we can also characterize where it happens. Okay, so what we discuss here is the characterization of the reconnection, place of the reconnection in this pathway. And there are many other pathways, and for each pair in arrows in red, we can give the unique characterization of the place where it happens. And the black one, we know example where it happens, but we don't know the characterization. There may be some other example. So I'd like to show you some picture. So this is the first step. If you start from this torus link, as a result, you have this torus knot or connect sum of this. And we can characterize the place of the reconnection. The reconnection happens here at the crossing or here. So it's not near, but if you have a reconnection this place, then you have this topology. And the next step, from here to there, and we can also characterize the band surgery, and we can say that band surgery is unique. But actually, so here, band surgery happened in this at this crossing, and you can isotope this band to here. So band surgery at crossing, every band surgery at some crossing is ambient isotopic to this one. So this is unique. And if you have a composite knot, a composite link of trefoil and hop link, then the band surgery is there. So this is also unique. And the next step, starting from this to this, so we have the uniqueness of this, but we don't know the uniqueness of this, but we know some example. So this is a picture, and starting from a connected sum of two trefoil, and if you have this link, this is one example, and we don't know the characterization. And if you have the connected sum of this, we know the characterization, and it should happen here or there. So this has symmetry, but up to symmetry, we can say that it's unique. Okay, and so on. So this is it is not easy to see, but it's an example here. So we know some example, but we don't know the characterization, and so on. So if you take a look at this example, many cases, the reconnection part is very short, but sometimes you need a little complicated. So this might not be happen or maybe happen, but sometimes you might need a little complicated reconnection. And in this case, we can show that the unique, so this is a twist knot, 5-crossing twist knot to Hopling and 4-crossing torus link. And in this case, the reconnection part is unique up to isotopy. And so on. And so, okay, we have, so, and this is a picture we have, and some of the reconnection can be characterized. So the reason why we get a good result for this characterization is that the first topology is a good torus knot link. In that case, actually, we can say that this type of the knot link is not easy to untie by reconnection. So you need, actually, in this case, you need 5 steps to do it. For example, if you have other orientation, so if you have a parallel orientation, so without orientation, it's the same link. But if you consider orientation, then those two links are different. And if you have anti-parallel orientation, we can easily see that you can go from here to there in one step by a reconnection. So the orientation is very important. Okay, so this is example, and so I skip this one. And I like to briefly mention that so actually I said that this kind of result comes from a recombination of DNA, and I like to just briefly mention what that can be applied to DNA case. So when you consider double-stranded DNA, you have this picture, and this is a picture of the unknotted DNA. And by idea of DeWitt and Klaus Ernst, we can use the information of the topology of the DNA before the recombination and after the recombination. We can give information how the recombination of DNA happens. And to model, so this is a schematic picture of the recombination of DNA. So this is a part of the double-stranded DNA, and that will be cut and connected in this way. So it is very similar to the reconnection of the vortices. So this is changed into this one. So this is a similarity of the reconnection and the recombination. So if you consider a mathematical model, you can use the same model to discuss. And for the DNA, do it have a very beautiful result on this area? And what I consider in this case is that so there is some experiment in 2007 where you start with DNA with this topology, and the recombination changed into a trivial knot or a link. And actually, by a experiment, you can see that the intermediate actually decreases the number of the crossing. So we can use the similar method to characterize this. So, and we have the result, so we maybe skip this. So we have the same result, and we wrote a paper in DNA recombination. And so that is the reason why we use the assumption that the crossing number goes down every step. So I don't know that is acceptable in this situation, but if you assume that the crossing number goes down every time, then we have a characterization of the pathway. Okay, so I will stop here and take questions. Thank you very much for your kind attention.